Presenter is Josh Eddy from Virginia Tech. We've had the pleasure of working with Josh now for 2 summers. He was with us last summer. We actually worked with him on a senior design project his senior year at Virginia Tech, so he's finished. His undergraduate work is behind him. And we've had the pleasure of having him with us here this summer. I want to draw your attention to 2 things that Jeremy talked about. One was state estimation, right? What is the state of my system? What is it doing now? What is it going to do? Or what can I predict that it's going to do? And he talked about sensors and data, right? How do we bring data in and how do we turn that data into information that's useful to us? And Josh has really been focused on this problem in a very specific way, and he's going to talk to you a little bit about that now. Thank you, Josh.
All right. Hello. My name is Joshua Eddy. I'm going to talk to you about this long, unseemly phrase. This is sensor fusion and position estimation for small UAS. So, navigation's tough, enough said. Navigation in any form for any kind of vehicle in most any environment is a challenge for a number of reasons. The obvious ones are sometimes we don't have GPS, sometimes our environment is rather misbehaved. We get all kinds of unexpected and usually interesting disturbances. The challenge is only exacerbated in the absence of things like GPS, where situational awareness becomes paramount. We are dependent on our sensor capabilities. Everything is about how we interact with the environment, how we actually see it. So, we are limited in what we can bring with us in order to see the environment. Small unmanned aircraft systems are uniquely predisposed to failures caused by changes in their aerodynamics. What that means in lay terms is that every time that we add a sensor, we are trading some amount of sensor capability for some amount of weight and efficiency and a variety of other things that impact the aircraft's performance. We have to be judicious in our selection of both sensors and computation hardware. Really, we're picking the absolute best stuff that we can put onto the vehicle and trying to engage in hardware minimalism. If we want more from our sensors, we must fuse them. The idea here behind my entire presentation, all of the work that I've been doing, and a lot of the work that's happening here at the Incubator is sensor fusion. So we're trying to take a number of different sensors producing disparate data, and we're trying to fuse them into one particular answer to the question, what is the vehicle up to? So really we could be saying, what is the system up to, and speak generally about any kind of system and any kind of stick for that system, but really our interest here is in small UAS. So we have been working, and when I say we, I'm talking about a number of PIs, plus myself, plus another intern who just left. There's a whole group of us who are working in this particular area, trying to fuse visual odometry, VO, with traditional inertial navigation systems, INS. So that really means we're trying to merge data coming from a camera with data coming from an inertial measurement unit. So inertial measurement unit, not unlike the one seen here. Inertial measurement units take a variety of different forms, but most of them are a combination of gyroscopes and accelerometers, sometimes a magnetometer, sometimes a barometer, sometimes a thermometer. But generally we're talking about accelerations and gyroscopic rates. So we're trying to fuse these 2 pieces of data to get them to check each other in order to form a better estimate of what our system is up to. So, in the process, we're trying to make this fusion simple and even scalable, which is the point of AON, which you just heard about. So, hardware solutions. I have spent a fair amount of my time here at the Incubator developing little bits of hardware that will help other people do the job of sensor fusion. We've designed multiple vehicles for indoor testing because indoors we have a lot of control over the environment. So behind me here are 2 such vehicles. We have this adorable rover with 4-wheel drive. The point of vehicles such as this is that we are able to drive them around on the ground, really. I mean, it's just so much stability that we get out of such a vehicle. I guess I should put this in front of the camera. A rover is really great in that it doesn't fall down. It does nowhere to fall. We are able to drive these around inside of our Vicon environment. We're able to do all kinds of things with them in a really controlled fashion, frequently using the exact same software or very similar software to what we're using on our actual aircraft system. And we have an example of an aircraft system. So this is the green machine. This is a vehicle that's been outfitted with a variety of different computational and sensor payloads. And currently you might notice that it has no props. And there's a reason for that. Step 1 in getting a vehicle such as this, flying indoors, flying in a controlled environment in a controlled way, is what we call hand flying, moving the vehicle around in the environment and seeing how the motors respond and how the software responds as it's moving around. So, we did this, but we need GPS sometimes. So, one of the things that I did very early on in my time here at the Incubator is I built a number of these GPS emulator boards. This is actually previous work performed by another intern who was here before me. He designed an entire workflow, plus this PCB design, for getting a GPS emulator radio system in place such that we could use Vicon in order to get ground truth and turn ground truth into GPS data, GPS packets. So this thing actually transmits what would be U-Block's binary GPS data to the vehicles in real time. So I designed a number of these. What this gets us is a lot of flexibility, and we don't have to actually change how the software works. We're still using GPS. It's just homemade. However, for vehicles that are designed to go to very different environments, we might have to deal with other challenges. On Mars, we don't have GPS. So in order to carry out autonomous mapping missions, which is one of the many functions of the Mars Electric Flyer, which you will hear a lot more about later, we need novel sensing modalities. So what you're seeing here is the Mars Flyer, and on the next slide I'm going to talk about why we need particular processors for our sensors. What the Mars Flyer is supposed to do when it takes off is actually take off vertically, and when we're taking off vertically, we would like to actually be able to still be localizing while we're rising up in the air. So we designed, you can see this little green thing in the picture, this is a mount for not only the computation payload, but also the sensor payload. So we loaded the Odroid XU3 computer into the mount, and we put a downward-facing camera underneath it. So we have a downward-facing camera such that when we're flying up and flying in VTOL or flying in vertical flight, we are still able to look at the ground, and we are still able to perform visual odometry. We are still able to use all of the computer vision methods that we have programmed in. The idea is that in the future we are going to add another camera that is pointing exactly at where you are right now, such that when we transition into forward cruising flight, we'll still be able to do exactly the same thing. Okay. So, your algorithm is only as good as your processor, however. You cannot offer anything more than the hardware is willing to give. So, we have chosen the Odroid XU3 as I mentioned earlier, and I want to tell you a little bit about why. It's an 8-core CPU that can run at a max of 2 gigahertz. It's actually 2 different CPUs put together, each of them 4 cores. The other one I think is, I'm not sure the other one is 2 gigahertz processing speed, but it's still a more than decent processor. It has an onboard 3D accelerator. It's got ample physical input and output opportunities for the addition of a variety of different peripherals. It's just an all-around good platform, and it comes in an extremely small form factor. So, the mount in close-up looks just like this. So here's the computer, and here's one downward-facing camera, and this face right here, which is currently left unused, would be used in the future for the mounting of another forward-facing camera. So, further testing in the field of sensor fusion is going to be centered around taking a rig, not unlike this one, which I just showed you, and running around and taking not only video but also IMU data. So on this little piece of hardware here, we have a Matrix Vision Blue Fox camera, which is a global shutter camera, and you're going to hear more about those. And we have a Fidgets IMU, which is a very fancy little IMU, which is a 3-axis accelerometer, a 3-axis gyro. It's a relatively vanilla implementation of an IMU, but it's of good quality. So the idea here is that we can run around with a laptop that has this plugged in, and we can take video and we can take IMU readings, and we can do this using DDS. We can do this using the AON network, and we can record all of the messages and other traffic that are coming from this sensor. And when we record them, we're then able to come back to the lab, and in the safety of the lab, we can replay this data in real time. So if we have an algorithm that is meant to turn this data into odometry, or to turn this data into otherwise into position data, or whatever it is that we're actually looking for, we can replay this data as if it's actually happening. For those of you who might be familiar with ROS, this is the same concept as a ROS bag file. This is literally replaying the flight you just did. So this is a huge boon to us in the lab setting. So, software is the other main part of my presentation. Our sensors are imperfect, but we're not throwing them out. Inertial measurement units, vision algorithms, GPS, everything that you can imagine implementing or putting onto a vehicle suffers from some amount of noise, and because so much of what we do on a vehicle is integrate data that we're getting, such as accelerations, which we can integrate to get velocity and then reintegrate to get position. When we integrate noise, we get drift. And drift literally means on a graph, you think your thing is drifting away from where it should be. So in order to handle the drift problem, we have to produce an iterative, self-correcting method by which to combine our sensor readings. Sensor fusion is worthless if we are not going to correct our sensor fusion in real time, or at least real enough time. So, Kalman filtering is a powerful approach to this problem. For those of you who aren't familiar with Kalman filtering takes the idea that I know the dynamics of my system, and I'm able to combine my dynamical equations with an understanding of the amount of noise that my system gets and my characterization of that model's noise, and combine these iteratively and robustly to get a better and better estimate of the system state. So, this whole approach provides us with a convenient and robust means of not only removing the noise, but fusing the disparate data, because we actually have in the numerous matrices that go into a Kalman filter, we have worked in the kinematics and the physics that say this sensor should mean this, and this should be applied to our acceleration or our velocity or whatever it is. We can actually combine these things mathematically in an intuitive fashion. So, I programmed one of these things, and I'm going to explain to you why I did that. This is example data produced using an unscented Kalman filter, which is one flavor of Kalman filter. There's numerous Kalman filters. There's linear Kalman filters, extended Kalman filters, unscented Kalman filters. There's a lot of these things. But this is an unscented Kalman filter running on a sample data set. The dashed blue line is the true state, and the red line is my estimate. Produced by filtering the data iteratively over about I think it goes from 1 to 20, 1 to 20 time steps. So it might actually look like my estimate is just going to 0 and then not moving anymore, but in fact it's actually responding in very, very small amplitude oscillation. Excuse me. So the idea here is that we want filters to become our tool belt. Batman's a hero, but the utility belt should be mentioned if we're going to talk about this. We really need a variety of different tools that we can go to, and we can go to conveniently in order to do any kind of sensor fusion for any kind of vehicle. So we want not only an unscented Kalman filter, but an extended one, and maybe a particle filter, and maybe an information filter, and all kinds of different methods of fusing our data, and we want to be able to get to them conveniently. And that's a problem. And here's why. Implementing a good filter takes time. Filtering, especially Kalman filtering, depends upon a variety of different kinds of expertise in disparate fields. Not everything is adjacent to everything else. You kind of have to know stochastic processes, you kind of have to know signal processing, you kind of have to know control theory, and you really better know linear algebra. All of these things are not unreasonable to expect from a researcher, but it is unreasonable to expect that somebody's going to be not only an expert enough in their field in order to think, hey, I need a Kalman filter for this, and then actually depend on them to go out and implement it all new, all over, reinventing the wheel for themselves. That's getting unreasonable. So the idea here is that I have designed a system, or have tried to implement a system, by which we can lower the already very steep learning curve. So, abstraction makes life easy in the software world. So what we have done is we have taken the already object-oriented, node-based approach of Aeon, and we're trying to apply it in the field of Kalman filtering. So I know how an unscented Kalman filter works. I know what the algorithm does under the hood, and I know what inputs it needs. So I'm responsible for the abstract side of this little diagram. This is my filter class. This is everything that I programmed in, and everything that you don't need to know about your system, how it actually turns into a new estimate, happens under the sheets right here. Everything on this side is in the researcher's domain. The way that the state moves forward, sensor data, noise and covariance, everything that characterizes the particulars of the system happens over here. And then, as long as all of these parts have been put together using good code contracting practices, they will fit together neatly, and we're going to be able to do business. So, here's an example use case. Jeremy already explained to you the node approach that Aeon takes. We're going to have topics, and we're going to have different services that are looking for those topics, publishing and subscribing, and we're going to have them all talking to each other in kind of a great big circular team. So here's one use case. We have a quadcopter. The quadcopter is carrying an accelerometer, a gyroscope, a magnetometer. It's got the whole IMU package, and it's publishing quadcopter sensor data as a topic. The filter node, which may be implementing a linear filter or an extended filter or an unscented filter or some filter that hasn't been invented yet, is going to be reading that data, and it's going to be producing quadcopter state information as another topic. The quadcopter controller is going to read the quadcopter state because that's its primary input, and it's going to be producing quadcopter controls, which will actually be the commands that the vehicle receives. And thus we actually complete this little circuit, which is, in kind of a simplified fashion, the outer loop controller for a vehicle. So that's what this means in the big picture. We are making this kind of data available, and we're making it sort of like one-stop shopping for a researcher trying to apply this to a small UAS. Future work is going to include implementing other varieties of filter, because all I've done up to this point is implement the unscented filter, which is a pretty good one to start with because it's relatively complex and there's a lot of stuff that can be abstracted away. But there's also particle filters and information filters. There's all kinds of things that can be implemented and added into a greater Kalman filter shell. The other thing that we should be doing is integrating this with pure computer vision methods and any other variety of sensor that we can think of besides normal computer vision means. We want this to be able to fuse seamlessly with any kind of data that we're going to produce. Well, I also want to investigate auto-tuning algorithms that could run in the background, because these filters, when they run, aren't perfect. You might have seen a couple of little blips where my filter didn't exactly follow the sample data. That's because my filter has absolutely no tuning whatsoever. It's completely vanilla, and it's basically identity matrices where real matrices with real coefficients should be. So tuning is important, but tuning also is not immediately obvious to the end user. So tuning in the background would be massively helpful. So there's an old saying, it takes a village to raise a drone. That is nowhere truer than right here. I'd like to thank Dr. Danette Allen, Mr. James Nealon, Dr. Locke Tran, Michael Eswine, who couldn't be here because he actually left already, who was my faithful partner in crime for fighting my way through Kalman filter literature, Gil Montague, who taught me how to program, I guess, and all of the Autonomy Incubator team. So thank you so much, guys.